So hello and welcome to our presentation on a critical analysis of feature and confidence-based outer distribution detection. This work was presented at the Unsure workshop at MICCAI 2024 on the 10th of October. So to introduce myself, hello, my name is Harry Anthony and I'm a PhD student at the University of Oxford under the supervision of Professor Konstantinos Kavnistas. I'm part of the CLAIM group. My research focus is on improving the reliability of deep neural networks for medical image classification. So, consider the setting that I'm training a deep neural network for medical image classification, such as diagnosing skin lesion images, with a set of images and corresponding labels, which makes up my training data. Once a model is trained, it could be applied to unseen images from the same distribution as the training data, which we call in distribution, or ID. But what happens when it's applied to an image which is significantly different from the training data, which we call outer distribution, or OD? Well, what we see is predictions on OD data are both unpredictable and unreliable. This motivates the field of outer distribution detection, where we want to detect an OD input and then defer the decision-making to a human clinician. Outer distribution methods typically give a scoring function to each input image. We can then plot the scoring function for each image in the dataset, and we can then place a threshold on the scoring function, and we can say everything below this threshold is outer distribution, and we can discard those predictions because they are unreliable, and everything above that threshold is in distribution, and we can keep those predictions. We can quantify the ability of the scoring function to separate ID from OD images using the metric area under the ROC curve, or AROC, which is a threshold-independent metric where the true label is in distribution and the false label is out of distribution. There is a growing body of work which is arguing that the outer distribution detection framework does not effectively detect errors. They instead propose evaluating methods on their ability to discard incorrect predictions, regardless of whether they're from OD inputs. Let's visualize the difference between these fields. On the y-axis, on the top we have in distribution, on the bottom we have outer distribution, and on the x-axis, on the left we have a correct diagnosis, on the right we have an incorrect diagnosis. Failure detection aims to separate along the x-axis, where we want to discard model predictions that we believe will be incorrect, whereas outer distribution aims to separate along the y-axis, where we want to discard predictions on images which we believe are from a different distribution from the training data. As with OD detection, for failure detection, we get a scoring function for each input image. We again evaluate the performance of failure detection using AROC, but in this case, the true label is a correct diagnosis and the false label is an incorrect diagnosis. Outer distribution detection methods can be put into two categories. The first is internal methods that use the outputs or parameters of the model trained on the task of interest, such as diagnosing skin lesion images. The other group is external methods, which are external to the model trained on the task of interest, and is a different model trained solely for OD detection. This can include one-class classifier methods and reconstruction-based methods. We can further break down internal methods into two groups. There's ad hoc methods, which require a specific type of network architecture or a type of model training. This can include Bayesian neural networks or outlier exposure. And the other group is post-hoc methods, which can be applied to pre-trained models. There are several benefits to post-hoc methods. They can be applied to pre-trained models. They're usually not dependent on the type of model architecture, and they're usually at a low computational cost. So all the methods we're going to talk about today are post-hoc OD methods. We can group the post-hoc outer distribution detection methods into two groups. The first group is confidence-based methods, which use the model's output layer for outer distribution detection. In our paper, we analysed 12 of these confidence-based methods, listed below. Some of these methods have hyperparameters that can be optimized on an external validation set. An example confidence-based method is maximum class probability, which uses the class with the highest softmax score as the scoring function. The assumption that this method makes, along with the other confidence-based methods, is that an OD input should lead to a high entropy output, where the entropy of a distribution is how spread out the probabilities are. So if the probabilities are evenly spread out over multiple classes, then the entropy will be high. The other group of methods we studied are feature-based methods, which don't use the model's output layer, but instead use a hidden layer in the model for outer distribution detection. And we studied the following methods listed below. Our analysis was completed on 2 medical datasets. The first is D7P, which is a dermatology dataset. To create an OD benchmark, we manually annotated this dataset into 2 subsets. Images with no rulers, which we use as our in-distribution cases, and images with rulers, which we use as our out-distribution cases. These labels are available on my GitHub repository if you want to use this benchmark in your own research. We then trained the model on 90% of the images with no rulers to classify between images with nevus and images without nevus, where nevus is a benign growth which has the potential to develop into melanoma. Once the model is trained, we applied the OD detection methods to try and separate the held out ID images from the OD images. And comparing the accuracy on the held out ID data to the OD data, we see that there is a 15% drop in accuracy. The other dataset we analysed was breast MNIST, which is an ultrasound dataset. Again, we manually annotated this dataset into 2 subsets, images without annotations, which we use as our ID cases, and images with annotations, which we use as our OD cases. And again, these annotations are available on my GitHub repository if you want to use these in your own research. We trained a model on 90% of the ID images to classify between images with a benign tumour, images with a malignant tumour, and images with no tumour present, which we are calling normal. Once the model was trained, the OD detection methods were applied to try and separate the held out ID images from the OD images. In comparing the accuracy of the held out ID data to the OD data, we see that there is a drop of accuracy of 14%. Right, let's look at the results. So on the x-axis, we have the outer distribution detection AROC, and on the y-axis, we have our failure detection AROC. This is for the breast MNIST task, where I'm showing the results for a ResNet 18 model, where I'm showing the mean of 5 seeds. So let's start by plotting our confidence-based outer distribution detection methods, then our confidence-based methods with an optimized parameter, and then our feature-based methods in green. What we see in general is the confidence-based methods perform better than the feature-based methods at failure detection, whereas the feature-based methods perform better than the confidence-based methods at outer distribution detection. We see the same thing for a VGG16 model, as well as for our dermatology task with a ResNet 18 model and for a VGG16 model. So let's go over some of our key takeaways so far. Firstly, outer distribution detection is not the same as failure detection. Secondly, we saw that confidence-based methods outperform feature-based methods at failure detection. We also saw that feature-based methods outperform confidence-based methods at outer distribution detection. However, we have some remaining questions. Firstly, why do these trends occur? And secondly, why does it matter if an outer distribution detection method is bad at failure detection? To answer these questions, we need to introduce two more tools. The first is layer-wise relevance propagation, or LRP, which is an explainable AI method. The idea behind this method is to indicate which pixels in the image contribute the most towards the model's prediction. How the method works. Given an image, we do a forward pass through the model. We then get the model's output, which we call the relevance. Layer-wise relevance propagation aims to redistribute the relevance backwards from the output layer to each neuron in the previous layer, which is calculated as the product of the weight multiplied by the activation from the forward pass, which is then normalized by the product for the other neurons in the same layer. This is done recursively from the output layer all the way back to the input image, which gives us a heat map like this. For the second tool, we created counterfactual data by synthetically removing the OOD artifact from each of our OOD images. This was done using intra-image interpolation, where we replaced the artifact with a patch from the same image. This was chosen over using a generative model or foreign patch interpolation for a few reasons. Firstly, it ensures we're not adding an unexpected OOD artifact to our image. And secondly, it ensures we're not changing the label of the image. We understand that this is going to introduce some bias, but we think this is a useful tool for approximately studying the impact of the artifact, both on the model's prediction as well as on our OOD detection methods. And all of these images are available on my GitHub repository if you want to use them in your own research. It's important to point out that we used a smoothing filter to ensure a smooth transition between the introduced patch and the original image. Let's zoom into the LRP heat map. Looking at the LRP heat map at the top, we see that the unsmooth transition is visible, which indicates that it's having an impact on the model's prediction, which we don't want to introduce. Hence, the Gaussian smoothing was necessary. Let's look at the results. On the top, we have our synthetic image without the artifact. On the bottom, we have our original image with the artifact. Looking at the LRP heat map with the artifact, we see that the ruler is mainly highlighted. This suggests it's having a significant impact on the model's prediction, despite the fact it's not even in the training data. To the side, we have the softmax distributions. Without the artifact, the model's prediction is both confident and correct. However, with the artifact, the model's prediction is now not only incorrect, but it does so with a high confidence. And this is really important to point out because, in fact, OOD artifacts can lead to high confidence predictions. This is counterintuitive, but it can happen due to several reasons. One potential reason is the model can learn correlations in the training data. And if an OOD artifact resembles a pattern, it could cause the model to give a high confidence prediction. You may remember earlier in the talk, I said that confidence-based outer distribution detection methods rely on the assumption that OOD artifacts should lead to high entropy outputs. Well, this example illustrates that that's not always true. And it's a key reason why confidence-based methods perform poorly at outer distribution detection. We can validate this result is true by looking at other explainable AI methods. However, I'm not going to go through all of these today due to time constraints. Here's another example where again we have the image without the artifact on top and the image with the artifact on the bottom. However, we have the opposite case here. The model's prediction is incorrect without the artifact, and the model is only correct with the artifact. And again, note this is a high confidence prediction. We can now look at the whole counterfactual dataset. We study the model's predictions on both images without the artifact and with the artifact, and we group them into 4 groups: correct regardless, incorrect regardless, correct only with the artifact, and incorrect only with the artifact. Here are the results for the breast MNIST dataset, where the pie chart on the left shows the predictions on the held out ID data, and the predictions on the right are for the OD data. We can then study what happens when we apply an OD detection method. We study the performance of both a confidence-based method, MCP, and a feature-based method, Michal-Nobis score. For our analysis, we first calculate the scoring function for each image using our OD method. We then calculate the 75th percentile of the scoring function for the held out ID cases, and we discard all diagnoses below this threshold for both OD and ID data, and study predictions above this threshold. So firstly, let's look at the results for our confidence-based method, MCP. What is good is we see the remaining diagnoses are now more likely to be accurate. However, what's not good is the percentage of OD images above the threshold remains high, and the percentage of predictions which are correct only with the artifact has actually increased. Now let's study what happens when we apply the threshold for our feature-based method, Michal-Nobis score. Straight away, we see the percentage of OD images above the threshold is much lower than it was for MCP. However, if we zoom in closely, we see what's not good is the diagnoses above the threshold are now less likely to be accurate. In fact, the correct regardless category has dropped for both OD and counterintuitively the ID data too. What becomes apparent is the strength of one method is actually the weakness of another. This motivates combining the methods. To study this, we applied MCP on the predictions passing the Michal-Nobis score threshold. What we see is diagnoses above the threshold are both more likely to be accurate, and the percentage of OD images above the threshold remains low. Although we're unlikely to see such a high accuracy in all cases, we argue that this is motivation that combining a confidence and a feature-based method can mitigate against the respective weaknesses. These results were also validated on our skin lesion task, which you can see in our paper. However, you may say, Harry, applying multiple methods means we're discarding a lot of predictions. What's the benefit of using machine learning when many of our diagnoses are being discarded? Well, my response will be think about how many people get medical scans each year. In the UK alone, more than 2 million women have breast cancer screenings each year, and more than 600,000 people have skin cancer checks. So therefore, using computer-assisted diagnoses tools selectively, instead of on every single diagnosis, would still offer substantial benefits. Another in-depth insight is OD detection methods with a high outer distribution detection AROC, which increase the risk of incorrect diagnoses, may not make my neural network predictions more trustworthy. And we saw this as a particular problem for feature-based methods. In fact, most outer distribution detection studies will only evaluate methods along the x-axis here. So my message to the community is if you're evaluating a new outer distribution detection method, it's important to evaluate for both outer distribution detection and for failure detection, so we can get a full picture of the strengths and weaknesses of a given method. The second in-depth insight is diagnoses which are correct only with the artifact can actually inflate failure detection metrics. Take the predictions above the MCP threshold. We saw that the ID accuracy was 92%. However, the OD accuracy above the threshold was higher at 96%. However, a large chunk, 32%, are correct only with the artifact, and instead the percent which are correct regardless is much lower. Well, why is this a problem? Well, we saw an example of a prediction which was correct only with the artifact before. We don't want to keep these types of predictions because they can give us a false sense of security, such as an overconfidence in the model's ability to handle OD data. For example, we can't guarantee that the performance won't break down post-deployment if the correlation between the OOD artifact and the correct diagnosis changes. Compare this to this prediction, which is correct regardless. We see here that the LRP heat map and the softmax distribution doesn't change when we remove the ruler. Clearly, we have a preference of the diagnosis on the left over the diagnosis on the right. However, if we're only optimizing methods to remove predictions which are incorrect, then we're not incentivizing methods to prefer the prediction on the left over the diagnosis on the right. And so my message to the growing body of research that's arguing that we should replace out distribution detection with failure detection is that failure detection framework doesn't consider cases when the model is correct for the wrong reasons. And this is a blind spot that must be considered. So, in conclusion, we saw that out distribution detection is not the same as failure detection. We saw that confidence-based methods outperform feature-based methods at failure detection, whereas they perform worse at OOD detection. We saw that OOD artifacts can lead to high confidence predictions. And finally, we saw that combining a confidence and a feature-based method into a pipeline can mitigate against their respective weaknesses. Thank you so much for listening. You can access my paper here, and you can access the data with the QR codes below. Please follow me on social media, and I'd be happy to answer any questions you have relating to this work. Thank you.